Good afternoon. Welcome to Kaapi with Kuriosity.
Do you want to put it in
I
my pocket?
invite Mr. Anand to tell you about the talk and to invite you all to the
Thank you.
venue.
It's on.
Good evening, one and all. Welcome to Jawaharlal Nehru Planetarium, Bangalore. It's my pleasure to invite you all for this session of Kaapi with Kuriosity. The title of the talk is The Mathematics of Soap Bubbles. We have Franz Pedit with us today to deliver the talk. So, as you know, these talks are arranged by ICTS in collaboration with Jawaharlal Nehru Planetarium, and it has been a long time from we are organizing this program, and this program attracts a lot of science enthusiasts as well as a general public. So, along with this, we have many other programs popular in popularization science and also the education programs at the Planetarium. So for all the details about the Planetarium programs in science education and also the science popularization, please visit our website once. So now I will request Madam to introduce the speaker of today. Thank you.
On behalf of ICTS, I welcome everyone. So, as you know, KWK is a joint venture of ICTS and JNP. And in ICTS, we have mathematics, physics, biology, etc. programs we run. And Professor Pedit has come for one of those mathematical programs. And he very generously agreed to give us this talk. So, Franz Pedit is a professor of mathematics at University of Massachusetts in Amherst. He was the co-director of the Geometry Analysis Numerics Graphics Lab and founded the GeometrieWerkstatt. His work centers on harmonic maps from Riemann surfaces using a combination of methods from integrable systems, Riemann surface theory, geometric analysis, and gauge theory. So I really welcome Professor Pedit to deliver this lecture. And before we start, we have a small little present for you.
Oh, that's very nice. Thank you. Thank you, Rukmini. Oh, nice things. I don't show you. That's special. Let's put that somewhere here that I don't forget it. Like here. Okay. So, thank you, the ICTS and the Planetarium, the outreach program, for having me here to give a talk. So I was told the talk is for at the level high school students. So I try to make it very elementary and sort of fun. And I have already been introduced, so I don't need to repeat that I'm professor of mathematics, of pure mathematics. So you will have to learn a little bit of pure mathematics today in order to follow the basic ideas. So we had a little glitch here with the technology. So I wanted to use my iPad, and I could write on it and project very, nicely when I write formulas or explanations. But now I have to do with the little blackboard here. So for those who are far back, they might better move forward, because that's the only space I have, and then I will have to erase every time I use it. I hope I have everything here. That's nice. Okay, so let's start out. So the mission is to explain some of these pictures you see here, and I think the Indian name of the object is Vada. Is that correct? Vada? How do you spell it? V-A-D-A. Vada. Okay. Vada is this donut shape. In the United States called a donut, or something little children wear when they go swimming. You've seen that, right? And I hope at the end of this lecture you will be believe, or at least understand, that this is a Vada. But it's not so obvious, is it? It's probably a very twisted and, badly things have been done to the Vada to get it to this shape. But anyway, so let's start out. So I'm a pure mathematician, and so there's a very famous 20th century mathematician called Sir Michael Atiyah, probably one of the most famous 20th century mathematicians, and he wrote many books and gave many lectures, but he also wrote this little poem, you could call it. So maybe I read it to you in the broad light of they mathematicians check their equations and their proofs, leaving no stone unturned in their search for rigor. Now the important paragraph, of course, but at night under the full moon, they dream. They float among the stars and wonder of the miracle of the heavens. They are inspired. Without dreams, there's no art, no mathematics, no life. So this encapsulates, I think, pure mathematics very, very well. And I hope today you get a little bit of an idea why some of us mathematicians are really most of the time spent on the second paragraph. Doesn't mean we sleep, but we imagine, we dream, we have, I wouldn't call it visions, but certainly intuitions and insights, which we then, since we are professional at the end of the day and write papers and have to produce results and get money, grant money and so on, we have then to check everything which we have dreamed up. So I think all of you know a very, very famous example, which is Ramanujan, the famous Indian number theorist, who claimed that a certain goddess told him while he was sleeping all these very intricate equations which nobody at that time believed even were true. And then he went, of course, to England and worked with Hardy, one of the most famous number theorists at that time, and Hardy carefully checked that all the equations Ramanujan dreamed up were actually correct. So this is a very good example, of course, which only a very few of us are privileged to experience, like goddess coming in the night telling us what we should do. Not so easy. Okay, let's keep on. So I want to talk about soap bubbles, soap films. And this has, of course, inspired humanity since you were able to make bubbles, and bubbles are even made on water sometimes, or many liquids do that. And especially as you see here, this area in the 17th, 16th, 17th, 18th, 19th, even 20th century art, there was many pieces of art which depicted soap bubbles. Here's a very famous one, and the overall theme of this soap bubble pictures is a kind of depressing one, because soap bubbles are so beautiful. If you have ever made one, they are there, and then they have these wonderful colorings, they float, but they're very, very short-lived. They die quickly, right? After this enormous burst of beauty, they're gone. So in some sense, all of these paintings, they have this underlying theme of the passing, right? Of beauty is only short-lived and then it's gone. So let's carry on. A few other examples. That's also a very famous one. Unfortunately, this painting does not exist. It got lost, so it was etched into a copper plate or metal plate, and then a poet wrote this underneath that etching. So also a little bit of a, it's not the most happy painting, right? So the statement that all riches, all honors, everything you can achieve in the world is all but soap bubbles, and meaning, they pop and it's all gone. Here's Manet, that is a bit more recent, well, it's mid-19th century, boy blowing soap bubbles. So in art, very represented. And then, as some of you perhaps know, in architecture, certainly nowadays, there are more examples than this. This is the famous Munich Olympia Stadium. And the architect, I think his name is Otto, somebody, I forgot, modeled these on soap films. So you will see later why these soap films, if you look at these pictures or this photo, why these soap films have this kind of saddle shaped, right? So one goes like this and the other side bends downwards. So they're not shaped like the bubbles, which are nice and round, they're shaped kind of like a saddle almost, if you look at that. So this difference, I hope I have time to explain. A few more reference to bubbles and soap films in literature. So this is Dostoevsky. Similar theme, as you can see. You know, he's sort of excusing himself or apologizing, not quite, saying, well, I'm not doing much, just sitting around, you know, playing, not much happening, and all my thoughts are like soap bubbles. Right? They float around, then they're gone again. And the lower one is, of course, from an American, Mark Twain, very famous, and he implicitly, of course, has a critique of capitalism. In the sense like, you know, if there was only one soap bubble, you know, you owned it, you would be very, very rich, right? Because it's so beautiful. All right, so maybe before we get into that, I had lots of experiments here. So around, I think, let me see, I think 18th century, a famous mathematician called Lagrange, French mathematician, posted that problem, and I could, I don't know whether I have here enough props, I wished I had. So, like this. So you can now see this. This is a, you know, I can bend it flat and it's like a kite shape, but I make it bend up so that it's like space, right? So it's a, imagine this is a curve, right? So it should stick here. So it's good. Right. You see, all see that? It's just a quadrilateral, so 4 corners. So you put this in soap solution. And the problem, of course, is I do real-time demonstration and they never work. But you see, this all falls apart already. So I can't even make this here. Let's try this again. The soap is so slippery. So I put this in. I pull it out. And now, of course, you should do that after the lecture. I was told I should pull it out with this handle, because then I have a better chance. Oh yeah, now it's in. You won't see anything. You have to come out. But there's a soap film spanned inside this boundary. It's very hard to see. And it's even very stable in the sense I can bend this, and then the soap film more and more approaches a saddle. Maybe I go to the first row. People can, now it starts coloring, which is a bad sign, because that means that the sort of degenerates. But can you see the soap film in there? See that? No, it's gone. You see, it was at the end of its life, right? So it's that. But the problem was you have some kind of boundary curve. So boundary. So this is a boundary, and these 4 things here. And you dip it in soap solution and pull it out, and this beautiful soap film forms. So if I were to do it here, what you see, you don't see much, but you see a disk. You just see a flat, like put a plate in, right? Maybe the first person here, you're a good pop, but it's flat, right? So but you can put anything, any curve. So let me use the board. So it's maybe a better thing. So you start with any curve in space. So maybe, so imagine this is a curve. No, this is a curve in space, a closed loop, something I can make, as I made before. Maybe I make it with, the wire business is very unsatisfactory, but you could model this with, you know, bending the wire and making some shape, like now I've made some shape here. You all can see perhaps, I don't know how well this is visible, but it's some very, you know, not very smooth. It has all kind of corners even here, and it bends around anyway, and then you dip it in. And hopefully, if you pull it out, it forms a nice soap film, right? And indeed, you do it right. And sorry, you can't really see it. You have to do it yourself after the lecture. I'm cheating now, it's already burst, but it will go in there and have this beautiful soap film spanning this curve, right? So let me try to draw it in. So here, somehow, this soap film will span into this curve. So just want to say, if you have questions, just ask. You don't even have to raise a hand. You can just loudly say stop, or I don't understand, or what is it you're talking about. So this was a problem posted by Lagrange in the 1750s or so, right? So Lagrange, famous mathematician. I write here Lagrange, right, 1750s. Not quite precise. And he posed this question, what is the property of such a soap film? You know, when he did these experiments and saw this, and he understood that the property is that the soap has a tension, surface tension. And you know about surface tension because you sometimes see little insects walking on the water. Though they don't drown, they hop on the surface of the water. There's a certain tension. And that tension pulls. And it wants to pull this soap film as small as possible. So it pulls it together. So it tries to minimize the tension. And it's easy to see if you're a physicist or biologist or material scientist that this surface tension is proportional to the area of the surface. It's a clear area, right? You measure how much area content. And so what happens is that these soap films minimize the area among all possible surfaces you could span inside that wire loop, right? So Lagrange figured this out. So these soap films minimizes area, its area. And I've said it now in words, otherwise I have to write so much. Among all possible other surfaces you can put in there. In around almost 100 years later, there was a mathematician, he was a physicist, Plateau, I think Belgium, around 1840s or so. And he did many, many experiments, and he formulated this then more carefully. It's nowadays called the Plateau problem. The Plateau problem means you come to me and say, here's some crazy curve in space, prove to me as a mathematician that there's really this beautiful soap film inside. Can you prove this? Well, of course I can say I can do the experiment, but you see when I do this experiment, sometimes works, sometimes doesn't work. So you have to do like I said before, the mathematicians have to prove something, they can't just dream it up. And so this was the famous Plateau problem. And the Plateau problem was solved in 1930 by, so this problem in 1930 by Douglas, the American mathematician. He got the first Fields Medal. So I'm saying this little history. And the Fields Medal, as some of you might know or not know, there's something called the Nobel Prize in physics, biology, in many sciences. But unfortunately, Nobel, who was a very rich industrialist like Tata, who was interested in giving money to science, his wife had an affair with a famous mathematician. So he excluded mathematics from the Nobel Prize. And it's a true story. So later on, another guy, Fields, said, well, these poor mathematicians have no Nobel Prize, so let's give them the Fields Prize, Fields Medal. So that's a very prestigious prize, which is given out every 4 years, and Douglas was the first one to get it for the solution of Plateau's problem. And I repeated, Plateau's problem say, give any closed curve in space, and it doesn't even have to be very regular. It could be, the simplest case is I could even take a square which has corners and dip it in, and pull it out, and you will see, you won't see, but you imagine it's there, the first row people can see it, this perfect soap film inside, and now it wobbles because there's wind going in, but it's right there, right? So you can bend it a bit, and then it, of course, deforms, but you can see it's in there, right? So it doesn't really matter how sharp it is, any curve you make will produce, and this is another effect which I will later on explain, built this soap film. And he proved this by mathematics. It was very difficult at that time, and even today it's a very difficult piece of mathematics to prove that. Okay, so this is sort of little history. So now let's involve the audience a bit. So are there questions to that? Is the problem understood here for soap films? You have a boundary curve and you want to span inside a surface, and the soap film minimizes the area among all surfaces which you can span in this boundary curve. Yes?
This is the mechanism by which cloth is
Sorry?
dirt from cloth is removed. The surface tension is...
Yes, okay. Yeah, of course, you probably know more than you should. So there are people in the audience who are math teachers, they were math students at the college, PhD students, physicists, biologists, technicians. They should not ask questions. Because it's unfair to those who are, for instance, just coming in because they were at the planetarium and they see a lecture and don't know mathematics. But let me do one lower dimensional example. So in mathematics, there's this, at the end, a lot of mathematics nowadays is done in very high dimensions, so I don't want to get into that. So dimensions 4, 5, 6, 7, infinite dimensions, and I don't want to discuss this. But all of us, when they study a problem, try to reduce it at least to 2 or 3 dimensions where we can visualize, we can see, or even lower down to 1 dimensions. So this problem in 1 dimension lower would mean the following. You have this is a 1-dimensional boundary, because a curve is 1-dimensional, because you can only go in 1 direction along the curve. The surface is 2-dimensional, because you can go in 2 directions on the surface. So now I could make a boundary which is just 2 points. Here's a point, here's a point. This is now my boundary. And I ask if I connect, I connect this boundary by a curve. No, chalk is not very stable. Here's a curve connecting it. The question now you could ask, previously we tried to have the smallest area. Now you could ask what? The smallest length, right? Yes? Who is here in high school or college, like undergraduate? There are a bunch, yeah. There are lots of them up there. Length, you understand length? Everybody? Good. So you can ask, what is the curve of shortest length? And you know the answer, right? Yes. Everybody knows the curve of shortest length. The solution is the straight line. So this minimal surface problem, 1 dimension lower, is very elementary. It asks for the shortest connector between 2 points. Yeah? And in 1 dimension up, this problem is much, much harder. Finding the smallest area among all possible surfaces. So, right, I have to erase, unless there are more questions. So let's do a few. Erasing is hard. So let's do a few examples, so to show you. And again, you should be part of this. So first, what was the color of my boundary? Red, I hope. So let's keep red as the boundary. So now I take as my curve, my boundary curve, just a loop, right? Here, circle. Boundary curve is a circle. I draw it 3-dimensional, so here it looks like an ellipse if I look at it prospectively. So boundary curve, circle, circle. So what do you expect? The minimum. Okay, so I missed one terminology. Since these surfaces minimize area, mathematicians call them minimal surfaces. Good name. Minimal surfaces. Okay? So I take this. What do you think the minimal surface, the surface of smallest area in this circle would be? Louder. The plane, yeah, it would be this disk spanned in there. We can do the experiment, and I think I've done it before. So dip that in, pull it out, perfect. There's a little bit of gravity, which of course we ignore in this problem. And we are not allowed to have wind blowing, and so you see this very nice disk, right? Can put its area to r squared pi, I think is the formula. Yeah, so disk is in there. Perfect disk. Okay, good, we are happy. So the answer is a disk. So how did I draw before? Green was the, or yellow, I forgot. What was the spanning thing? Maybe make it yellow. What was it? Blue? Green, make it green. So here, disk, I write. Disk spans and all others, that's actually not a proof, of course. So you say disk clear. Why is it clear? I could perhaps put another surface in, which bulges up a little bit, bulges down a little bit, maybe does something strange, maybe this has smaller area. But no, it doesn't. You can prove this is the best, right? Disk is the best. Okay, so it's the disk. Now I can do something more interesting. I brought 2 of those, and now I have to use my hands, dry them, otherwise a mess. So I have 2. This would be Disha. How do I do this? I put it in. So the idea about what do I want to make? I have one boundary here, a circle, a second boundary here, another circle. Now I put them both in. And see, what do I do once they're in? I slowly pull them. Can you do it? And I explain. Does it? See, can you see? Can anybody see anything? I pull them apart. What happens? Some surface forms beautifully. It gets slimmer in the middle, very fashionable surface. Then eventually breaks. Right? So let's try it again. Come out. It's not easy to do these things. I mean, you should do this by yourself. Maybe afterwards, play with it. I separate it, pull it up. There's an extra thing. Disha, you would have to pop it. It has an extra thing in it, right? Okay. Now it's there. Beautiful surface forming. And now it gets very tricky because, did you see? Okay. So, this is a problem for you. So what do we have now as our boundary? 2 circles. Okay, let's do 2 circles. Here is a circle. Here's the same size circle. My drawing is perhaps not so great. And then we get this beautiful surface. It looked like this. Right? The surface had this shape, right? You all agree? Looked a little bit like maybe a cooling tower of a nuclear power station. Looked a bit like this. So I show you a picture of it that is much nicer than my drawing. This is it. So you shouldn't be too, this is a more correct picture because what I draw here was not quite right. It should have a much slimmer, what do you call that? The area here, neck perhaps. If it's here, what's it down here? Waist is good, right? So it should be more or less like this, right? So it's more accurate. And you have seen this, right? Okay, so this is the surface. So it's this surface of revolution, what mathematicians call surface revolution, because there's one curve, like this curve, and then you imagine there's this axis straight through the center of these 2 circles, and then you rotate this piece, this arc around. Then you get this. And if you're a potter, then you know very well, potter has a wheel, and how they make the cups, they just push their hand in a little bit, and then all the way around it has the nice intention, or they stretch it. It's called the surface of revolution. So this is a minimal surface. Now, why did it pop? When I pull these 2 circles further and further apart, it popped. You saw it pop. It didn't pop because the soap was at the end of its life. It actually popped. But what happened was that this went further in, now I'm exaggerating, and then at the end, it sort of almost had you see what I mean? It almost had a singular point, like a cone tip, right? You could see it actually. I don't want to do it again. You can do it yourself. My question to you is, why does it pop? Why does it do this? What happens? Not from material science here, but from the idea of a minimal surface. And what did it pop to was the question, right? If I do it again, what happens is, I don't do it now, I just show it. I have this nice surface, I stretch it, and then it pops, and if the soap film was stable enough, it would make two discs. So it would, you understand? So what happened? Think of smallest area. So when I push too far away, the surface I'm making has more area than the two discs. Yes? So I repeat this. Is that clear to the students? So at some stage, you can compute this actually. Even high school, or even I say, you can compute it. Now, you might be interested to know what is this curve here. You could guess, but it's a quite famous curve. This object is called the catenoid for a particular reason. No, I don't have my patch. Do you have something? I mean, I would have to, yes, there you go. You have some right ideas. I would have to steal the necklace of your wife and so on, but I don't want to do this. Sorry, that would go too far, right? See, that is in fact the profile. Mathematicians can prove that. And what is this curve? A catenary. It's a chain hanging curve, right? And it's described in mathematics by the cosh function, right? Cosh, cosine hyperbolic. I don't know whether everybody is familiar with these calculus things or not, but it's a cosh curve. And as you know, the cosh curve has the property that it looks very quickly like the exponential function, and so that's why this looks so flat when you go further out. So if you look at that surface, it does go out to infinity when you continue, when you make the circles I'm doing my experiment larger and larger, the surface will not stay between two horizontal planes. It will just extend all the way out to infinity, but it goes very, very flat when it goes further out. So this is the famous catenoid. Now let's see. I don't think, can I make the Disha, you promised I can make the helicoid? Probably not. So there's another surface I show you I can't make, which is the helicoid. So what is this? This is a winding staircase. So how does this surface, how is it made? You have in the middle a line, and then you have a horizontal line. Do I have horizontal lines? Yes, here these things. It's a horizontal stick. And you have seen this winding. So here's a vertical line, and then you turn this while you go up. Understand? You go constant speed up and constant speed turn. And that makes this surface. Again, when you are very close to the center of your winding staircase, it looks a bit like this. But if you go further away and make a bigger piece of the surface, it looks like this. It looks like a parking garage, very flat. And then in the middle, there's something interesting happens, namely this. Right? So this is also a minimal surface. And now, of course, this does not have the link for some reason. So there is a very nice, I don't know why it's not here. I had a link, I can't show you. Oh, maybe I can. There it is. Do you see this? You see this. So there is a nice deformation between the catenoid and the helicoid. They are related. So I'll show you that. So here's a helicoid, and you will see this in a loop. So it becomes the catenoid, and then it opens up. There are all minimal surfaces in between, becomes the helicoid again, and then it would come down, become the catenoid again. So it goes between the catenoid and the helicoid. There's this nice, mathematicians are very excited about this because they can connect these two isolated surfaces by a whole family, right? There's a smooth family connecting the helicoid with the catenoid. So now how do I go back to where I should be? So we can close this. And now what do I do next? Where is my presentation? It's gone. No, it's here. Don't be worried, it's here. So this is a minimal surface. So I'll show you examples of such things. Here's a very interesting one. This is called the Riemann staircase. There was a famous mathematician around the 19th century, 1820, born, died very young. He was not quite 40, but his legacy is still people still do research in problems he posed. So he's probably one of the most famous mathematicians after Euclid or so. Everything we nowadays do in geometry and also in physics and many things come from Riemann. And this is Riemann's staircase. So how does Riemann's staircase look like? I can't make it for you. It's very complicated. Well, not too, but I can try to make it. But how do you do it from the catenoid? Well, I go back, pull this out, maybe I can. And then what did I do? I separated these up. But now I can pull these, shift the two circles. Can everybody see that? I'm shifting these circles. See this? And now it's popped. But this is exactly what happens. This catenoid gets shifted, and then it makes a nice, it fits into a plane again. So this is, you should think this is a plane. So you get this stack of planes, and in between you have these shifted catenoids. So Riemann found this example. And this example is also very interesting because it has limits. So I'll try to explain that. So if you put these catenoids, these tubes a little bit further apart, right, like here, then what you start seeing is they're like a stack of catenoids. They just have catenoids stacked on top of each other. And when you move these tubes closer together, like here, then what do you see at the end? You see two helicoids. Here's a helicoid, and here's a helicoid, and they are oppositely turning, and they are connected. So this is the perfect parking garage, because you can go up along this helicoid to your parking deck, and the other cars can come down on the other side. You know, so such structures have actually been built. So this is probably one of the most famous minimal surfaces, because it also relates this catenoid and helicoid all in one go. Okay, so questions to these surfaces. So I want to say these are intricate, difficult. Even mathematicians took about 100 years to really understand these surfaces. They have many, many properties. So one nice property is whenever you slice these surfaces horizontally, intersect with a horizontal plane, you see a circle. Different radii. So you can here see, when you slice here, you would see a line. When you go further up, you see curves, circles, 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 and a line, circles, circles, circles. So it's a very intrinsic, interesting shape for mathematicians. So there was another attempt. Remember the helicoid? So some people thought, can I make a tube, like in the Riemann example, you have a helicoid, can I connect one level of the winding staircase with the next by putting a tube in? And that's possible. Took a long time, done in the 1990s, 2000, people understood how to put tubes into these things, but you can't do it in a catenoid as a proof, so people didn't do that. This is an equally famous surface, it's called the Costa surface, and you can, by now, hopefully get a little bit of an idea how these surfaces are kind of intrinsic, what structure they have. This surface has two what people call catenoidal ends. See, the top looks like a catenoid, the bottom, it looks like a bottom catenoid, and then there's something interesting happens here, and this end, if you extended the surface very far, is planar. It looks like a plane at the end. So this is a surface with one planar end and two catenoid ends. That was a long, open question. Do such things exist? Yes, they do. So we have that. Oh, now I have to not do this. Okay, so this is soap film stuff. And I haven't done this experiment. So here's a trefoil knot. That's a nice space curve. Look at that. If I dip this in, pull it out, of course I see a beautiful minimal surface. I also have to pop. Now it's popped. And inside is a wonderful minimal surface spanned by this very intricate curve. So you have it. So you can just do any curve you like. And I invite you afterwards to come out. I can put in anything. I can put in, for instance, a little roof shape. Makes this wonderful, rather complicated looking minimal surface. And there's no end to these shapes. Tetrahedron, right? Here it is. And it's hard, a camera on it would be really nice, then you could see it beautifully. But there are many YouTube videos where you can see these things. So this goes on forever. So many, many minimal surfaces. Now we are talking about soap bubbles. That was our objective, right? So I've talked about minimal surfaces. So what these minimal surfaces minimize the surface area. So now you might say, what happens if I blow a soap bubble, right? So I can clearly do that. Put this in, hopefully this works. And then, no. Oh yeah, there it goes. Lots of soap bubbles. See how they go. If I'm lucky, the big ones are hard but in principle, you see they break. Yeah? Maybe I'm too violent with them, but see they break. They're too heavy, right? But the little ones work well. And it doesn't matter what you do. Here's a square shape, put it in, pull it out. Soap bubble, right? So it makes soap bubble all the time, right? Whatever I do makes a soap bubble. So why, right? Why is this so? Why, when I put in this square shape, it wouldn't do something different, right? Make soap bubbles. So the question is, can you make a soap bubble as a minimal surface? Remember what a minimal surface tries to do. So here's a nice bubble made out of soap film. And a minimal surface, what does it try to do? It tries to have the surface area as small as possible. Now, what would happen if a minimal surface were a soap bubble? It tries to make the surface smaller. So what happens? The bubble would shrink, right? So if the soap bubble were a minimal surface, it would just become, you would see it get smaller and smaller and add up as a point. So a soap bubble cannot be a minimal surface, right? That's sort of a proof, right? So you can't have a soap bubble so that the soap film is a minimal surface. So now I have to see. So how much, we start a little bit later, so what's the time I have exactly? Yeah, I have 15 more? 22. So now we have to do a little bit of mathematics to understand this, right? So you might ask, okay, I'm telling you these nice stories and I show you a lot of pictures. And the question is, how do mathematicians actually check that an object you're seeing here is a minimal surface? How do you do that? You can't just dip some object in a soap, pull it out and compare to the thing and say, aha, it's a minimal surface. You have to really have a criterion, right? So now we do something, since we deal with surfaces, which is called elementary surface geometry. And as you look at these surfaces, they all curve, right? All these interesting surfaces curve. They were not just planes. There was one example was the plane, but all other examples curve. Get the idea of curvature? Curvature is one of the most fundamental quantities in life, period. Because when you look around this room, well, you see flat pieces as walls. That's just because it's built like this. But if you look at your neighbor, it's not flat, it's curved, right? Everybody's curved. Cars are curved. The universe apparently is curved according to Einstein and so forth. So everything is curved, like these pieces of curves, curved, funnel, curved, everything is curved. So curvature is a very important quantity. So let me explain curvature. And like mathematicians do it, they start on the very elementary level and build from there. So this is now an exercise I do with you. So I draw a circle. Circle has a radius. What should the curvature of a circle be? You have to make a decision. It has something to do with the radius, right? If the radius is very, very big, what should happen to its curvature? Should it be bigger or smaller? If the radius is very, very big, then the curvature should be smaller, right? Because if a circle has very big curvature, radius, it looks almost like a straight line. Let's start with the straight line. Maybe I was already too advanced. Here's a line. What's the curvature of a line? You agree on that? A line should not have curvature. It's not curved, it's a straight line, right? K is equals to 0. Curvature is K. Happy? Good. Go to the circle. What's the circle? Radius r, radius 5. What should be the curvature? 1 by 5. Huh? Reciprocal of the radius. That's, I think, a reasonable thing to do. The circle has curvature 1 over radius. You might debate that. Why is it not 1 over radius why not over square root of the radius? Why not over 1 over radius squared? Why 1 over, so you can think about this. I'm not going into this. It's 1 over radius. That's the correct answer here. So, but now comes the difficult question. Not every curve is a circle or a line. There are lots of curves which I've shown you which weren't circles or lines. So here I'm drawing one. Here's a curve, right? So, what would you call, so what happens on a line? If I'm here, the curvature is 0. If I'm here on the line, curvature is 0. That means the curvature is 0 everywhere on the line. The curvature of a circle is 1 over r, everywhere on the circle. You get this? The curvature doesn't change when you go around the circle. One says the circle has constant curvature. It doesn't change. But what happens here? Do you think the curvature changes when I walk along this line? You say yes, because you probably know all that. So the curvature changes. Now, I invite you to do, children do this, but you can do it yourself. You go somewhere where there is a road which is exactly like this. You get yourself into a car. You go 50 miles or 50 kilometers an hour. And you don't have no brakes. It goes 50 kilometers an hour, and you have to go along this track. What would happen? Right? When you come to the first turn, pretty tough, right? You would feel something. Here, we're fine. It's almost straight. So you nothing. Here again, you have to turn maybe less bad when you turn the curve. So somehow these acceleration forces, or what you call them when you're in the car and you turn, they roughly measure curvature. So, but how do mathematicians do that? So what would you say here? It's curved, here it's almost flat, here it's curved again, less so, maybe curved again, less so here. So what mathematicians do is the following. They want to use that they understand circles. So they say, okay, here I sit. This is my point. I want to compute the curvature of the curve at that point. Clearly, the curvature of this curve at this point will be different than at this point. Here it's almost 0, but here there will be probably curvature, right? And so how do you do it? Well, the prescription is simple. You choose 2 more points. So this is the point that compute curvature. Then you choose 2 more points on that curve. And then I hope everybody knows that if you give 3 points in a plane, there's a unique circle. So there's a unique circle connecting these 3 points. And then you do calculus. What does calculus tell us? We should move these 2 points into the yellow point. And every time we move it, we compute the circle. Find the radius. And lo and behold, if you do this process by moving these 2 points to the yellow points, so now you're erasing them, there will be a perfectly fitting circle, and its radius is 1 over this radius is the curvature of this curve at that point. This was a bit much, right? But remember calculus. Does anybody know calculus in this room? What do you do in calculus? You do the following. You have a point, and you have one other point. Then you take the secant line, and then you let this point move in, you get the tangent line. This is Newton. This is probably the achievement of mankind in the 17th century. This is calculus. And from that on, we could do anything, right? Fly to the moon, to the Mars, outer space, doesn't matter anymore. We can do everything. With this simple idea, what's the tangent to some curved object? Curve, right? Calculus. But then you can go a little bit more advanced. You take 2 points and let them move in. Then you get a limiting circle. And that limiting circle has a radius at that point. So let's call this point P. Point on the curve. And so we have a curvature. So this is the radius at that point P. And then we compute the curvature at P, array kappa, or K at P is 1 over radius at P. So this rather involved construction gives you a measure of curvature along this curve. So if you did this at that point and try to fit in, do the same construction, it's almost flat. So this circle will be very, very big. And hence the curvature here would be 0 along here. Probably roughly 0. So curvature here is curvature at this point, Q say, is roughly 0. And then if you traverse the curve in a certain way, like going this way, then you notice that there's a difference whether the circles are sort of below your movement or they are above. And so there is a sign. So here, by our convention, the curvature is positive on this part, so now I use different color. Red for positive and maybe green for negative. So here the curvature is positive all over. Then here will somehow become 0. That's the famous inflection point on the curve. And then over here, the curvature becomes negative from here on. It's negative curvature all the way to here, inflection point, positive curvature. So you can see there's a sign. So I don't want to get too much into detail, but this curvature of a plane curve has a sign. Okay, great. So now we understand curvature of curves in the plane. How do we do curvature of a surface? Then we go up. I saw the thing, yes. So, okay, let's do that. So now we have a surface. I draw a surface. Here's a piece of surface. So, surface has, so here's the point, I want to compute its curvature. So what every surface has a normal line, right? So it's the surface, then there's a line which is perpendicular to the surface. And now there's something you can check. There are exactly two planes which contain this normal line. I draw them here. There's a plane here which cuts out a curve through this point. So imagine there's this vertical plane hitting the surface, and then there's another vertical plane, maybe like so, hitting the surface, and that cuts out another curve in this plane. So two perpendicular planes, it's like when you open a book, right? And these two planes contain two curves. So I can compute the curvature of the orange curve here. So they call that K1 at P. And then it is the curvature of the green curve, K2 at P. And then I can add to the arithmetic mean. So this is called the mean curvature. So H equals, I drop the point, so it's a half K1 plus K2. So this is called the mean curvature. So now we've done real mathematics. And then there's another quantity called capital K, and that's the product of these two numbers, and that's called the Gauss curvature. So famous mathematician Gauss did that. So we won't do this. So this is a curvature measure. And what Lagrange, I think, together with Gauss proved is a surface is minimal if and only if this mean curvature is 0 over the whole surface. Not just at the point, thanks, everywhere. So what does that mean if the curvature is 0? That means that this curvature at that point of this curve is exactly minus the curvature of the other curve, because these two numbers sum to 0. That means kappa 2 is equals to minus kappa 1 at each point. And what does that mean? That means if you look at the surface, you see one curve bending this way in that point, and the other curve bends away. So you see a saddle type surface. That explains that, so this little exercise explains that when I put in a shape like this, it comes out as a beautiful saddle. Right? So I try it again, maybe this time it works, but I stick it in, take it out, and lo and behold, you have this wonderful saddle-shaped surface. So the surface, here it's pretty easy to decide what's kappa 1 and what's kappa 2. So kappa 1 will go along this way and kappa 2 along the other way. So you have this wonderful saddle here. Some people might see it, right? So this saddle-shaped surface, which is made right in there. So this explains that. Now, let me move on to soap bubbles. So you have seen this effect a little bit. I want to do it again, perhaps. So what happens if I move this very fast? Did you see that? What happens? Wind blows into it because I move. Is that clear? Wind blows in. What does that exactly mean? That means that the pressure of air, right, is a little bit higher inside than it is outside because I have moved it. That's the same as blowing. Like, unfortunately, maybe I have this. Is this blowing? It is. But how do I do it? Well, maybe I can't. Now I got soap in my mouth. But maybe this blows. So usually people blow. There, I've blown. What is this? Where do I blow? Oh, here. Here we go. So I'm blowing. Could you see that? So I'm blowing air in, and so there is a slightly higher air pressure. And of course the thing, and then it closes up, so inside the bubble it has a little bit more air pressure than outside. And the effect, and the air pressure difference is exactly this quantity here. Can prove that. Is that sort of clear? For a minimal surface, which is a soap film, the air pressure from above and below are the same. So the soap film has this mean curvature 0. But if you make a soap bubble, then there's slightly more air pressure inside than outside. And so this H, or mean curvature, will not be 0. It will be exactly the difference of the two pressures. So it's a constant mean curvature, not 0. And these are the soap bubble surfaces. They are constant mean curvature, not 0. All right. So now you can ask, do you have any examples of such surfaces? So let's maybe write this down. At least write a little note for ourselves that we don't lose this train of thought. Right? So soap bubble surfaces have mean curvature H. So mean curvature. So the sum of the principal, these kappa 1s and kappa 2s are called principal curvatures, have H equals constant over the surface, but not 0. The minimal surface has it everywhere 0. This surface has everywhere mean curvature constant, some constant. So let's do an example. Let's take the sphere. Here's a sphere. Because of course the sphere is the soap bubble. So we believe this should have constant mean curvature, right? Because we see it. We blew it. We made it. So now do my prescription. I draw the vertical line, and since a sphere doesn't matter, it looks the same everywhere, I might as well draw this normal line at the North Pole. Then I take a plane, intersect, so you take some plane, maybe this plane, and intersect. So what I see is this piece of circle. Then I take a perpendicular plane, and intersect, I see this piece of circle. So the kappa 1 is 1 over r, because this has radius r, this sphere. And the kappa 2, or the curvature 2, is also 1 over r, because they're two circles, same radius. So this means the mean curvature of this is 1 over r. Right? It's 1 over r plus 1 over r divided by 2, because it's a half. So now we have no more electricity, but this seems to still work. Right? Okay, so the soap bubble is constant mean curvature. Happy. Okay, so let's see what I have here. It's a bit bad. Now we are degenerating. Something is coming. So the mathematicians have figured out, and this soap bubble, of course, you've seen the pictures, existed around the time of Lagrange. He understood this also. Soap bubble has constant mean curvature, not 0. The next question was, do you have any other example? And then there was a mathematician called Delaunay, and he asked, are there other examples? And of course, one example you can do, it's hard to see, is the cylinder. I just draw this, a big cylinder, tube. And I do the same thing, I do the normal lines, they are up here, make the slices, and then I see two curves. One slice is the straight line, the other slice is this tube circle, and so the mean curvature here is 1 over 2r. Okay, That's also constant mean curvature surface. These were the only ones known up till the mid or later 18th century. And then Delaunay came along and asked, are there more of such surfaces, which are surfaces of revolution? So if can I have a profile curve, take a line, rotate, and generate a surface? What is that? That's a beautiful answer he got. You have to do the following. You roll an ellipse on a line, and you follow one of its focal points. See that? So an ellipse rolls, generates a profile curve, and then you rotate this around that axis. And he proved this is a constant mean curvature surface. You can also roll a hyperbola. Much more interesting. Hyperbola rolls. You see, it goes all the way that it becomes the asymptote, and then it carries on. And it generates this profile. Also a constant mean curvature surface, he proved. And here are the pictures of these two. This guy rolling an ellipse and rotating is called the undaloid because it's wavy, and this is called the nodoid because it has these nodal curves. And here's a little video. This should be a cylinder. Not quite, almost. And then you can see how these surfaces again are related to each other. See that? So the cylinder turns into the nodoidal surfaces, then a chain of spheres, and then it becomes the the nodoidal surfaces. So these are all surfaces of constant mean curvature. Here's of course the ending or the crown of the lecture. So that was the stage of mathematics in this area until 1985. Nobody knew another example. Sphere, cylinder, and these nodoids and undaloids called Delaunay surfaces. These were the only known examples of surfaces of constant mean curvature. And people call them soap bubble surfaces because a soap bubble is, like that, right? So this was it. And then the big question has been, thank you, comes back, has come up. Are there surfaces of the type Vada, right? Vada type. So I should end with this. So let me erase this. So now I had prepared another, not prepared, but if I had the time, I would do a short course in topology versus geometry, but we don't have the time. So the question was, can you have a soap bubble of Vada type? So there's sphere type, which looks like this, and then there's a Vada, which looks like this. So now you can do, all of you can actually now easily, hope if you have understood my construction of mean curvature by taking a normal to the surface and computing these perpendicular planes and their curvatures, you can check this object does not have constant mean curvature. It has outside here positive mean curvature, somewhere inside in there's a line where it's zero mean curvature, and further inwards gets negative mean curvature, generally. So there's a shift. So this is not, the Vada you make at home does not have constant mean curvature, right? So there was big conjecture actually, or there were two main important theorems. Mathematician calls them theorems, so now it goes again, theorems. So one theorem was by Heinz Hopf. He proved that if you have any potato-shaped object like this, so a badly shaped sphere, just some potato, and if it has constant mean curvature, it has to be the round sphere. This is a theorem. If it's any such thing can never have constant mean curvature, it has to be round. Was one proof by Heinz Hopf. So this is Hopf's theorem. And then there was another theorem by Alexandrov at the same time. This was all in the mid-60s, 1960s. Alexandrov, Russian mathematician. And he proved if you have a surface of constant mean curvature which is embedded, which means it doesn't self-intersect it, like the Vada, these are embedded, it don't intersect themselves, then it has to be a round soap bubble. That is Alexandrov's proof. So these two together, mathematicians thought, well, that's it, right? These theorems strongly suggest the only surface you can possibly make of constant mean curvature is the round soap bubble. There isn't anything else. But that's not true. In 1985, Henry Vente, he produced what's called the Vente torus, and that's this thing here. So this is a constant mean curvature torus. Torus means donut, Vada shaped, which abstractly looks like this. But by that I mean you take this guy and start, maybe you have to cut it somewhere, and then you start doing things to it, moving in the inside, outside, intersect many times, and eventually you get this surface. So that's the Vente torus. And that has the intrinsic type of a Vada. It is not a sphere, it's not three bubbles stick together, it's really a donut-shaped surface. And you see that better in the next movie. Well, this is a different one. This guy is called Dobrina surface. It looks more complicated. Also a Vada. It's not a Vada you might make at home, but it is one. And here's a picture of how it goes. Let me stop the pic. So look at this. So what you see here, so it's probably a good demonstration. This curve you're seeing here, this beautiful curve, almost like when you splash milk, these slow motion pictures, but doesn't matter. This curve is one of these curves along which you would measure the curvature of the plane. So this is a planar curve. It's a bit thickened, but the black thing is a planar curve. And that's one of the curves of your Vada. So the Vada has two curves. It has, let me do this here, it has one curve going this way. Why do I never have enough talk? Here's one, and then it has a curve going this way. The two essential curves on a Vada, like this curve and that curve. They're very special because the Vada, of course, has bulk. Don't take the bulk, just the glazing, the top of the Vada, right? Or if you have a donut which has sugar glazing, just the sugar type, not the bulk, right? Not the dough. And these two curves are sort of now drawn when you map them as a constant, when you try to make constant curvatures. So one of these curves is this curve. And then in the video you will see the other curve, which is orthogonally attached, which is this curve. And then this curve can be moved around here. And now you see why this is a Vada, because it's the product of two circles, right? They're not circles, but they're closed curves. This closed curve, Cartesian product with this closed curve. These are two closed curves, and they kind of go around just like the Vada and make a Vada, right? So let's try and see this. So now this curve moves like beautifully along the first curve, and then now it's the animation. The other curve moves beautifully along the second curve, and then you see how the whole surface was built, right? Now here it is, right? So this, and then you can even deform the surface, right? So this becomes now more intricate. I don't want to explain this, but these surfaces have deformations, and so now it's a little, it becomes psychedelic. It's very hard to understand the interior life of this Vada. Now, the theme of soap bubbles bubbling off. But you can pretty much see that that I'm not lying. This is a Vada-shaped surface, except it's very, very intricately put together. And I don't know, here see many, many more examples of these guys, which some of them really do look like you take a Vada which is thin enough and then bend it. Here trefoil Vada, figure 8 Vada, twisted figure 8, rattlesnake Vada. Lots of them. So I think I'm at the end of this, and I don't want to get into this now because my time is completely up, right? It is up. So this would be another part, but I wanted to close this with something, so I just go through. Okay, if somebody asks questions, but what I want to put down is for you, because your culture has, of course, produced this, right? And all of you know this, right? You learned this probably in kindergarten, right? This is the creation hymn from the Rig Veda. And for every Western philosopher from the time of the Greeks, if they knew that, all the way up to Schopenhauer, Kant, name the greats, and many, many people who do this pure mathematics or pure physics, theoretical physics, this is probably most profound statement of human thought, of thought or creation as such, and I would say creation, period, right? I mean, and this is encapsulated by this creation hymn. And I guess what everybody, I think, including me when I first read that, was utterly, surprised or completely taken was this last paragraph, right? Where the statement is, whence this creation has arisen, perhaps it formed itself or perhaps it did not. The one who looks down on it in the highest heaven, only he knows, or perhaps even he does not know. You see that? That's, I mean, all of you probably, you learned this in kindergarten. I hope you do, right? Because this is this element of doubt, right? This is a statement of doubt. You do not believe anything. And that's the mathematician's mind. If a colleague comes up and says, this is true, my first instinct, I have a counterexample. You must be wrong, right? That's my first instinct. That's what mathematicians do. So we doubt everything, right? And then this beautiful hymn, of course, is in fact, it just tells you have to doubt. You cannot believe, doubt everything. And if you do, if your mind functions like this, if your thought process, then you will perhaps discover something which is beyond thought. Right? I mean, that's of course here not a promise, but you can think of it that way. Right? There is something where thought happens, but there is certainly something out of which thought comes. And mathematicians usually, I say that at the end, if there is such a stratum where thoughts end, there's no more thought, we are not quite there. The mathematicians work just above there. Pure thought. And, but maybe if you're old enough, then you go to the Himalayas, sit in a cave, and then you get to this strata where there's no more thought and pure creation happens, right? That's probably what I should end with. So thank you. Water. So if,
Please raise your hands for questions.
Oh my
I'll
God.
bring the mics to you.
My question is, if the mean curvature is constant but
Yes.
negative, would that also be a soap film?
yes, so I have, with this low tech here, not always succeeded in my best explanations, but remember when I said, when we have the curvature of a planar curve, I said it depends how you traverse it. If you and another way of saying it, so maybe I'm allowed to draw another picture here. If here is some curve, instead of saying which way to traverse, you can put a normal vector along the curve. So this is always perpendicular to the curve, right? So this is the normal vector. And then you can see that there's a sign. When the normal vector, when the normal vector points into the circle, you can call it a positive. And when it points out of the curvature circle, it's negative. So you get also this sign. And so likewise, when you then do mean curvature on a surface, you have a choice which side of the surface you look at. There's the normal points out this way of a sphere, for instance. You can outward normal or inward normal. And when you change this normal, then in my definitions of how I compute mean curvature, it will flip the signs of everything. And so you get negative. So it is the same, right? Make no change in the geometry, no change in everything I do. It's just my, what you call, conventions, exactly.
No question. So, with this Vende's torus counterexample, what did Hopf and Alexandrov not cover in their?
Say that again. I haven't.
Okay, so I was trying to understand. So you said Hopf and Alexandrov had given some theorems.
Hopf and Alexandrov have given two theorems.
Got
Yes.
it. And they were like about the minimal, so the curvature of the minimal surfaces. So
These were theorems about the constant mean curvature
Constant mean
surfaces.
curvature
Yes,
surfaces.
not zero mean curvature, but constant mean curvature.
correct. So then Vende's counterexample did something else. So what was that Hopf and Alexandrov did not
Okay,
cover.
I explained this again. This was a bit fast.
Yeah.
Hopf's theorem said, so maybe if I'm allowed to, it's just if I can erase a little bit. So this goes into something which I haven't really explained very well. But you see, in the field we are working in, geometers, topologists, there's two objects. One is called topology. And topology means topos, which means position, location, and logy means study. So it's a study of positions or locations. And then there's geometry, which means geos means earth, and metry or metric is all from the Greek, means measure. So there's one side where you just care about the shape. You don't care about how the distance is on that shape. So for instance, in topology, if I draw something like this, so it's a potato or whatever, this is for topologists the same as this. It's just rubber geometry. You know, imagine a rubber balloon, you can just deform it. Is it clear? You can stretch it, squish it, can do. And likewise, there's another thing, which is that, you know, this donut surface, but of course, a topologist would also consider a cup. Do I have a cup with a handle here? No, I don't. But but this thing is also a donut. It can be deformed, right? I mean, I can just put here a big nose and something like this. Also a donut, right? It's a Vada, but a badly made Vada, right? So it's a little thing. So these topologists don't care whether you rubber geometry, you know, deform and so on. But geometers do care. So these constant mean curvature surfaces, they are really metric. So they have distances, they have curvature. So all has to do with measuring things. Whereas here you measure nothing. This is rubber geometry. You can just stretch it. You're not allowed to cut it and destroy it, but everything else you can do. So Hopf showed that whenever I have an object in space, which is what people call sphere type, right? It could be like this. Then if it has constant mean curvature, it has to be the round sphere. This guy could also have had self-intersections. You can imagine I make this very long, carry on, and then I move it back and, you know, somehow push it back and it comes out again. So it goes into itself. So Hopf didn't care about that. So everything which is sphere type I call it, is round. Is a round soap bubble. And Alexandrov proved something different. He said any surface, it doesn't matter whether it's Vada type, sphere type, or more complicated, two Vadas stick together type, which looks like this. Any surface of constant mean curvature which has the type of these with maybe no hole, one hole, two holes, three holes, doesn't matter, and is embedded, which means it looks like this, it doesn't intersect itself. Then it also must be the soap bubble, the round bubble. Right? So who asked the question? You. It must be round. So then the question was, if I had now a Vada type surface, does it even exist? If it exists, it can't be embedded, because Alexandrov proves it has to be a sphere. So it cannot be embedded. So it must have very complicated internal structure, if it existed. And people didn't quite. There was camps in mathematics, 3 probably. There was one camp who believed they don't exist, another camp tried to prove they do exist, and there was another camp who said, I don't care. And then the camp which tried, it does prove it does exist, succeeded. Wente was the man who proved in 1985 or 1984 the existence. And that was the beautiful golden thing you have seen here. So that has a long after story, of course, which I'm not going into. I mean, they're all beautiful other surfaces, but you know, here it is. That's the Wente torus. And you can see it's not just 3 bubbles like golf balls stuck together. You can already see this very intricate internal life, where sort of the tube of the Vada snakes around inside. Okay, does this answer your question? This is what Wente proved, right? So.
Actually, I have 3 questions. First,
3. This might go a long time.
So, are there any practical applications of soap films, and is this a surface like what you're showing has it been realized in practice, or is it like too complicated that it cannot be?
No, I mean, what do you mean by realize now?
Like
As a soap film? As a soap bubble?
like, does it manifest in practice, or it's only a theoretical computation?
When you say manifest in practice,
Yeah, like for example, the Klein bottle or the Mobius strip.
yes?
It can be manifested in practice. So this, does it exist?
Yes, it exists.
Okay.
Here, look at it.
Okay. But can we like touch and
You
like,
can build it.
oh,
You can build it on a wireframe. I mean, students do that actually. There are a bunch of places on this world where, as undergraduate students, as their final project in geometry, they are told, make this.
okay.
And they make it.
Are there any practical applications
Of this guy, I don't think so.
like the entire soap films in general, like the mathematics of soap films, like has it found applications?
The soap films you have seen have actually a lot of applications. I mean, the simplest, of course, show you architectural applications. But so that's, I've explained that the soap films, you can, we can, I mean, I don't mind, but the other people, everybody can leave, of course. Don't be polite. If you're tired, just, there's somewhere tea or water or cookies or whatever, so run and get before anybody else gets there. But I've explained that this mean curvature is the difference of pressure between inside air and outside air. But this happens also if you have two media and you have an interface between two materials. You see what I'm saying? Two different molecular structures have an interface, perhaps, like oil to water, oil to air. Then that interface is, to first order at least, modeled by a consuming curvature surface. Modeled by it. So this interface layer, right? So, and that's, I say, first order, because usually in this, in material science and biology, say, when you think of a drop of blood or something, or they have certain shapes, but they also have a certain elasticity to them, and that's an additional property which I have not discussed, which is not captured by mean curvature constant. It's a more complicated effect. But to first order these interface layers between different materials have, on a molecular level, you can go microscope, I haven't shown any of these pictures here, they have shapes of consuming curvature surfaces. But mostly it depends, of course, what molecular structure you have, what kind of which ones of these appear, right? Is it just, if the sort of the pressure or whatever you model here is the same, then it would be like minimal surfaces, soap film type, or if the pressure is different, then it will be one of these. But since it's a surface layer, you will never see this closed object. You will see a piece of it. You see what I'm trying to say? You won't see all of it. You will see some piece as an interface layer. In praxis, I mean, it's not like the surface is infinitely extended. This doesn't exist in real life. Yeah. So they do have applications, definitely.
And are they in any sense bounded by the physical principles?
Yes.
Like for example, if we do these experiments on Jupiter, which has got more gravity and different ambient pressure.
Yes.
Will the surfaces be also?
I think you could have, if you work in astrophysics perhaps or something. There are, in fact, there is, you know, perhaps Penrose, a famous physicist, and he worked on black holes, and there's some theorem about black holes where he used a consuming curvature, so in this case a sphere, around the singularity, and then he proved certain things which I don't exactly know. So they did appear in astrophysics. Yeah. So I don't know about Jupiter and the various gravity and so on, but the mathematical model of these is I haven't spelled out. I have always said you blow air in it, so there's slightly more pressure in it. But mathematically, you could model this by saying you have a given volume, right? You tell me volume 8 or 7 or 5 or a chunk of volume. And now I want to enclose it. And I want to enclose it by smallest surface area. So what I do, I minimize area, but I have a volume fixed inside. So that prevents the bubble from shrinking. You see, so that's why it makes a nice round bubble, because there's volume inside and I fix the volume. And that is the physical principle. You minimize area by fixed volume. And then you can translate this in probably physical terms, other ones. Right?
Thanks. Thank you.
Oh, there's somebody here. There's somebody, then somebody in the back, and then there was you? Were you also? But you're the third, right? What about you, sir? So. Oh, please, can you have him add a comment? So, because otherwise we disconnect.
I just wanted to add to your question and the discussion. So, I have a friend who is a civil engineer, and 30-40 years ago, they would actually have soap bubble labs. So sometimes what would happen is that the surface that they want, it's too difficult to compute. So they would make wire frames, dip it in soap, and then measure to see what exactly the shape is. So that's an actual application of where they would use it.
Yeah, that's true.
Is it possible to have a soap film on a Mobius strip?
You mean on? Yes, you can have a Möbius
How
soap
would
film.
it look?
Sorry, you can make it.
Like if you have.
Yes, you can. You see, the Möbius strip has a. Have you ever made one out of paper?
Yeah.
Yeah, you take a strip. We have lots of paper here, but I'm not allowed to cut this into million pieces. But I would have to cut it. But anyway, so you see, so when you make a Möbius strip, this is a cylinder, but you would turn this, and then that's the Möbius strip. It's a bad Möbius strip. But the Möbius strip has one boundary curve. You probably, some people know that it's not two boundaries, it's one side, one boundary curve, and you can have a minimal surface bounded by this thing. Yes, you can have
And
a minimal
also,
surface.
what's the curvature of a 90-degree bend? Would it be infinity?
Yes,
90 degrees?
if you do a 90-degree bend, then they have that gets tricky now. But yes, naively you would have a singularity in the curvature. And then the easiest, before you bend, maybe you just bend a curve, right? I'm drawing a corner simply, I show you a corner here, right? There's many so clearly, I mean, you can see this here. I mean, clearly, I always say it's not so clear. I mean, all of these things are not clear, really. So here's a square, right? Everybody sees a square. Clearly, curvature 0 along the straight line, curvature 0 here, but then there's a corner. What's the curvature at the corner, right? Now, this becomes interesting because, I mean, some people think, curvature is, I didn't quite explain that, but I did say it has a little bit to do with acceleration and how the tangent or the normal to the curve twists. And so here it flips by 90 degrees. So maybe this is curvature a quarter or something. So you see, but a good intuition is this a singular point in this kind of geometry, and you should perhaps assign infinite curvature at such a point. Yeah. So there was somebody in the back, if you.
So you were talking about Lagrange and how we used soap. Yeah.
Sorry, yes, you are now. Okay.
Yeah. You were talking about Lagrange and how he was using soap films to understand principle of least action, correct?
To understand what?
Principle of least action. I mean, Lagrange came up with principle of least action.
Oh yeah, principle of least action.
Yeah.
Lagrange. Yes.
So while talking about soap films or soap bubbles, we talk about minimization of surface area.
Yes.
But do we talk about minimization of energy or minimization of time, or is it interconnected to minimization?
That's correct. So when you say energy, what energy do you mean?
The energy that might be required to form the surface area, perhaps? Form the surface area.
What?
formed?
Yes. If I understand, I repeat the question. So the question was, I have, if you are more knowledgeable perhaps about all of this, I do something which has to do with least action. Least action. Now in physics, action can be anything, right? Action could be time sometimes. What's the least amount of time it takes to go from here to here under gravity? What curve do you? There's a famous Trachystone, I think is the name, is the shortest path. So many things can be action. And then I think your question was, is there some, so area could be action, right? The area could be, so action is a very general concept. Lagrange actually has started that. And then you can have area is a special example of an action. Right? And so my Lagrangian, as physicists would call that, is the area, right? And I'm minimizing the area. So that means I try least action means smallest area. Then another, I think the next question you said is also has to do with energy. And yes, there's a slight difference between area and energy, but there's also an energy measure on a surface. There's a certain quantity, people call it Dirichlet energy by another French mathematician. But this is very closely related in this sort of geometry to the area. In fact, it's equal to the area up to some constant. So energy and area are the same in this case, right? And so I'm really minimizing area or energy, a certain energy. But for these guys, I don't just minimize the area, I have a constraint. And the constraint is volume. Right? So this is, of course, do you study physics or something? Yes, so then you are very familiar with that. I mean, like if you do classical mechanics, you have Newton's equation and they would tell you if there's no force, you will go along a straight line. But of course, if you constrain your problem to laying on a sphere, then of course you can't go on a straight line. You have to move on a geodesic or something on the sphere. That's a constrained problem. So you still have zero force, so to speak, but you now are not living in Euclidean space, but on a sphere. And that leads to this notion of geodesics and so on in mathematics. So yes, so that's actually a good question. Yeah. So does this help you with an answer? Yes, I do Lagrange action functional minimizing. Yes, exactly.
Okay, so let's say you have the catenoid.
Yes.
Right. And then you're, let's say, the two circles, you just infinitely start moving them farther and farther away.
Yes.
Does it form a Gabriel's horn, that curvature?
Does it?
Form the Gabriel's horn. The Gabriel's horn, it has infinite surface area.
What's it called? Gabriel's horn?
Yeah.
I don't know what the Gabriel is. That some?
It's like.
Yeah. No, it does. I mean, it actually doesn't. I mean, the thing is that this is another interesting thing. I showed you. Maybe I should show you the catenoid again because it's so. Let me see how quickly I can go back to the catenoid. Probably I go the wrong direction. So, just because your question was the catenoid, there it is. So. If I do this experiment, which I have now attempted so many times, and it has mostly worked, I pull it, but I have my radii here fixed in this experiment. If I want to make this shape, I would take probably these two large circles, and that would make this surface. You see the large boundaries? And I could make these circles larger and larger, and then the surface with more and more surface. But even if I go out to infinity with this, the surface area is 8 pi. The total area of this is 8 pi. 8 pi. That's it. Strange, isn't it? It's not infinite area, it's 8 pi. You could compute it. I mean, mathematicians have a little bit of insight here because I've told you about these catenoidal ends. And so each catenoid end contributes 4 pi to the area. And so you have 2 and so on. So you get some idea. And that I showed you the Costa surface, I think. So that's a bit more difficult. So it's not so easy. Helicoid, of course, is helical is a bit more tricky, but where was the costa? So this guy here. When you can see it has a catenoidal end up, down, so there's at least 8 pi, and then there's this planar end, which usually also adds 4 pi. So I'm not quite sure whether it's exactly 12, but I don't know exactly. But there is, well, what would you call it? You know, if you know Lego, the children play, or toys, and so you have a certain intuition that they're pieces stuck together, but they are, of course, they're not, you can't just stick them together. It has to be perfectly smooth to make this soap film. So you could, and that's actually a difficult part of mathematics. Some people do try to construct new examples by taking old examples and gluing them together. And if you, I can show you one trivial example, not trivial, one examples which were very difficult to construct actually, and have taken a long time to make. So we have learned that, for instance, the sphere has constant mean curvature, and I compute. So this is a sphere. And then we had seen these undulating and delanoidal surfaces, right? And so you can get, it's too big, the sphere. So you can get the following idea: make a sphere here, and then I put more spheres up here, and maybe down here, sphere, here is sphere, and then I'm attaching these undulating surfaces, like so. You see, just do Lego. I have this stick, like, you know, like a stick like this, but it's a surface which looks like that. And then I have a sphere, and I just stick them together, like children would do. And I do this down here, and everywhere I stick, and here I make a connection here, here, and here, everywhere. And then I get a surface which has, people call it a hole here, hole here, hole here. People call it a 4-hole surface. But is this constant mean curvature? Well, it is here, but not where I glue it together. There it fails to be. It's a brutal gluing. And then there is a very, very difficult piece of nonlinear analysis, it's called. Very difficult piece of mathematical perturbation theory, they call that, where you can actually prove. But if you make these necks small enough and you have enough of these bubbles, then you can actually make it smooth here. Well, that's a very, very, there are papers which are 100 pages long, and there are like 3 or 4 of them, and that has been now understood. It's a very, very difficult piece of geometric analysis is the type. So I just wanted to elaborate here that, you know, you can, if you understand this subject enough, then you could have these ideas of taking known pieces, stick them together, and then prove by perturbation arguments that these surfaces exist. Of course, this is now going far away from your answer, do they have finite area or not, and so on. Yeah, okay.
So I'm sure all of you have more questions. We can ask Professor Franz the same questions outside near Kaapi. Let's thank Professor Franz Pedit for the
thank you.
talk.
Okay, thank you for coming, and it was enjoyable, somewhat for me. I hope for you too.
The Kaapi will be just right outside. I hope to see